Here's a video about how to approach optimization problems that are quadratic in a pre-calculus class. So I just start with an example, and before you even do the algebra to solve it, I want to talk about the big idea of what this all means. So here's a situation. We've got 35 feet of fencing, and we want to make a rectangular pen that's cut into two parts. So first, let's understand how to build one of these pens. Here's one possible way of doing this. Notice that I have the length 13 feet and the width 3 feet. If you add up all the fencing, the right-hand side is 13, the left-hand side is 13, the bottom is 3, the top is 3, the middle is 3. If you add those up, you actually get 35. So this is an example of a type of fencing that the problem is asking for. And if we figure out the area, it's just length times width. The area is 39 square feet. So that's one example. Let's make a different one, right? I have this one on the left-hand side just so we can remember what we did. Here's another one, just made it up. I went ahead and made it 6 feet by 7 2/3 feet. If you add up those 5 sides, you actually, again, get 35. So it's the same problem, just a different way of doing it. And if you figure out the area of that, 7 2/3 times 6, it's actually 46 square feet. So this one's actually bigger, a better area. It's better in terms of the fact that we want a maximum area. And let's do another one. This time I made it 8 feet long and 5.5 feet high. Again, everything adds up to 35. That area is 44 square feet, not quite as much as the 46. And so these are the 3 that we've done. There's actually an infinite amount, and we've only done 3. So the big question is, all right, we got a maximum out of these 3, but is it the maximum out of all the different infinite possibilities? And so that's what I want to talk about, is how to attack a problem like this with algebra. So some steps. With any word problem, we of course draw the picture and label it if possible, and we can with this one, so we're going to. Remember, here's our problem, and then label it, a width and a length. First step, that's it. Second step, and this is really important, I like to talk about the focus of the question. A lot of students get caught up in the wrong part of the problem. In fact, if you start playing with the 35, that's the wrong thing to start playing with. What we care about is what we want to minimize or maximize. And in this situation, it's area. So our focus is the area formula, and that's actually pretty simple. Area is just length times width. That is our focus. Of course, we're sad because we want to be able to find a vertex. You'll find out that's what we want to do, but there's 2 variables, and so we can't do it. So we need to fix that one. That's what step 3 is about. And sometimes, honestly, the focus you'll end up with is already in terms of 1 variable, and you're happy and you keep going. But if it's got more than 1 variable, we need what I call a constraint equation. And that's usually where the other information comes from. Now I'm going to focus on that 35 feet. And my equation is if I add up 2 W's, right? There's a W on the right and a W on the left and 3 L's, a top, a bottom, and a middle. If I add those up, I end up with 35. And so this is my constraint equation. I'm going to use that to substitute into the focus. So again, this is the focus. There's my constraint. I'm going to solve for one of the variables. It doesn't matter which. I think I'll solve for W. And then I'm going to take this and plug it in to the focus equation. So instead of writing W, I'm writing 17.5 minus 1.5 L. And I end up with a formula for area, and it's got 1 variable. So I am ecstatic, because now I can just find the vertex based on what I've studied previously. Before we actually do that, let's make sure we understand the graph of what's going on. If I want to graph this function here, it looks something like this. Notice normally you have y equals, I have area equals, so the y-axis is actually area. Of course, normally it's x, but in this situation it's L. So L is the horizontal axis. And that vertex up there, we're looking for this point. It's going to give the maximum area. The maximum area is going to be the y value of that vertex. A little side note, notice it's got an x-intercepts of 11.667. What's that about? Well, if you think about it, if this length is 11 2/3, all 3 of them will add up to 35, and you won't have any more fencing to do the left-hand and the right-hand side. So it doesn't make sense, which is why the domain for this function is less than 11.667. And of course, it has to be bigger than 0 because it's a length. Anyways, let's go back to the problem. Here's our formula. We can find the vertex by using our negative b over 2a. The maximum is at L equals negative b over 2a. Plug it in, I get 5.833, and that's what L is. It's very important to know what your variable is, because the question is, what is this 5.833? Is it the area? Is it W? Is it L? You know it's L because the formula is about L. And then we just need to plug that in to get the maximum area, and we're done. It's about 51 square feet. Back to the graph, just to, again, understanding things graphically is really important. So what we just found, remember we found that the maximum occurs at L equals 5.833. We found out that the area was 51 roughly. So that's the Y value there. If you actually plug it in, that's the maximum area. We already knew that, but I just wanted to show it to you graphically. And here's the picture of our pen. By the way, where did I get this 8.75? It came from, if you remember, we found out that W was 17.5 minus 1.5 L. I just plugged in my L to that formula. And that is the one that gives the maximum area. We know out of the infinite possibilities, this is the one that gives you the maximum area. So just to have this in the video, these are our 4 steps. More videos are coming.